All right, today we're going to talk about the condensed states of matter, liquids and solids, gases as well. We'll talk about all the phase changes that are occurring from one phase to another, what actually boiling point is, and how to kind of analyze a phase diagram. And so there's kind of a lot to unpack here with this stuff, but here we go. First of all, the idea, you need to remember what kinetic molecular theory is. Very simple idea that the faster molecules are moving, the higher their kinetic energy. So that's kinetic molecular theory, basically saying that molecules are just randomly bouncing around. They have elastic collisions for gases, that is. And again, the faster they're moving, the higher their temperature because the more energy they actually have. And again, so kinetic molecular theory explains the properties of gases. And we talk about liquids. And typically things that are liquids at room temperature, they have a little bit higher intermolecular forces holding them together. And so they're free to move around each other, but they're attracted to each other. Getting a good example there are just water molecules. And so since they're close together, they're not compressible. So liquids and solids are not compressible. Gases are, because the gases are just bouncing around the container. They're about 1,000 times further apart than a solid or a liquid. Like I said, remember, you need to know what the different phase changes are. Vaporization is, again, going from a liquid to a gas. Evaporation, it's the same thing, essentially, just two different terms for describing going from, again, it's not boiling, but, if water is just it's on your skin, if you're sweating, for instance, and those molecules are turning to a gas, then that's evaporation or vaporization. And so it says, which of these would evaporate faster, water at 10 degrees or water at 40 degrees? And again, if you understand kinetic molecular theory, you understand the water molecules that are at 40 degrees are moving faster, so it's more likely that they escape each other. And so they can, so that would evaporate faster. And also keep in mind, a lot of this stuff is, I guess maybe it's hard for some people to kind of grasp the different changes that are taking place with the surroundings when molecules are either sticking together or breaking apart. Evaporation, if you're sweating on a hot day, the water molecules on your skin will start to break apart because it's hot and will evaporate. But when you break them apart, it requires energy to do that. And so it gets the energies from the surroundings, which is your skin, so it takes the energy away from your skin, so it has a cooling effect. And so that's why sweating allows you to stay cooler on a hot day. And misters, if you go to a restaurant on a really hot day, you see those misters or something like that, they actually work because, again, they're little water droplets falling, and when they're evaporating, they're breaking apart. They get the energy from the surrounding air, and it cools the air by about 20 degrees. Condensation is the opposite of that. It's going from a gas back to a liquid. And so in this case, think of it, the molecules are moving around as a gas, and when they slow down enough, they stick together. But now that they're sticking together, it would violate the law of conservation of energy if they didn't release energy to the surroundings. So condensation has a heating effect to the air. So when things are sticking together, it releases energy to the surroundings, heating up the surroundings, and when you are breaking things apart, it cools the surroundings. Moving on to solids, again, as I said before, one thing you have to understand, solid molecules have really strong intermolecular forces holding them together, and they, again, are not compressible because of that. Want to elaborate a little bit more on changes of state and what boiling point is and vapor pressure. Because if I ask you what the boiling point of water is, for instance, a lot of people would say, 100 degrees, but that's only at standard pressure that's true. To understand what would cause a liquid to boil, you need to understand vapor pressure. And a vapor pressure of a liquid is determined by the nature of the liquid and the number of molecules bouncing around the container. So if this is water in this, and those molecules that start to escape the liquid, they're bouncing around the container, that's what applies vapor pressure. And so the vapor pressure of any liquid in a container would be determined by possibly two things. First of all, the nature of the liquid. Water molecules, remember, have hydrogen bonds holding them together, so they stick together very well, and so you wouldn't have many escape. And so if you don't have many bouncing around, so water has a low vapor pressure compared to other liquids because the water molecules don't escape as a gas very well. The other thing that would determine vapor pressure is the temperature, because if we heat this up, more and more will escape, and so vapor pressure is determined by the nature of the liquid and the temperature of the liquid itself. And what boiling point is when the vapor pressure of the liquid equals atmospheric pressure. That's when something will actually boil. Some liquids are volatile. You want perfumes and cologne to evaporate really quickly. So they have very high vapor pressure. So if we put some type of cologne in here, they have very weak bonds holding them together. That's why you put them on and you want somebody to be able to smell them from a distance. And so they evaporate really quickly. So if we capped it, there would be many, many molecules bouncing around because they have weak forces holding them together. And so your volatile liquids, things that evaporate quickly, have high vapor pressures. A good example also is gasoline. If you ever pump gasoline in a car, it doesn't take you long to smell it because it evaporates quickly. Ammonia as well. So I want to revisit what boiling point is. I said it's when vapor pressure equals atmospheric pressure. So if we took the lid off of this, and let's just say this is water at 40 degrees, we could actually make it boil. Because what's happening when you take the cap off, the atmospheric pressure, all the gases are applying pressure to the top of this that are above it, keeping it from actually boiling. But if we lower the atmospheric pressure, in other words, if we took air, if this was in our room, and we took all the air out of the room, at some point, when the atmospheric pressure gets lower than the vapor pressure of the liquid, all of those molecules will start escaping. And so you can look it up, you can YouTube it, you can make water boil at a much lower temperature if you just take all the air out of a container. And it's when, again, once you have vapor pressure equals atmospheric pressure, that liquid will start to boil. So that's why if you're boiling water in Denver, the Mile High City, you don't have as much air above you, and water, instead of boiling at 100 degrees, might boil at like 96 degrees. It would boil faster, but it would take longer to cook because it's actually cooking at a lower temperature. And pressure cookers work by, if you increase the pressure, you can actually then keep water as a liquid at a much higher temperature and cook something with it still being liquid water at a higher temperature, so you can cook something faster. And here we're talking about, it says which one of these would have the highest boiling point. We already talked about this in the last set of notes. Is the one that has, again, the hydrogen bond there with it. Both of those molecules are polar, but it would have a higher boiling point there because it's got a hydrogen bond. And let's see, water molecule would have an even higher boiling point because it's got two hydrogen bonds in it. And again, look at further phase changes, the difference between freezing and melting. Freezing obviously is going from a liquid to a solid. So think about what's happening. It's going from a liquid where the molecules are bouncing around to a solid where they stick together. And when they stick together, then so freezing itself actually releases energy to the surroundings. A lot of people don't believe that, but when you get these really cold spells like we had, back in February, people that in the valley that are growing like citrus, they will actually go out, a lot of fruit and vegetable growers will go and spray everything with water right before it gets really cold. And so they do that, and they'll continue to spray it with water because even though the water freezes, let's say it's on the outside of an orange, it freezes on the outside of an orange, it actually releases energy and keeps the inside of the orange warmer so that it doesn't freeze. But this only works when the temperature is close to freezing. Like when our extremely cold temperatures, it's very damaging to crops and stuff like that. Let's see, melting point again, or melting itself is going from a solid to liquid. I think everybody knows that, but maybe these two you might not. Sublimation and deposition. Sublimation is going directly from a solid to a gas. That's what dry ice does. You go get solid carbon dioxide, it'll go directly from a solid to a gas. Example of deposition would be going outside on a really cold day that's actually dry and you see frost on the car. Because frost, you see the different patterns that it makes. It's not just water that's freezing to the car. It's actually going directly from a gas to a solid, and it makes nice patterns because of hydrogen bonds that are holding them together. All right, last thing, you need to be able to analyze the heating curve and understand what's going on in a heating curve. So this would be the heating curve for this one's for water, but it could be any liquid that's a pure substance would have this heating curve, and you have to understand what's going on. And so here's the thing, this is temperature here, time there. Notice the melting point of water is 0, the boiling point of water is 100. This is in Celsius. And so if you put a block of ice on something that's very cold, or I'm sorry, we'll take the block of ice, we'll cool it down to negative 40 degrees, and we'll just throw it on the table. So as you throw it on the table, the molecules in that block of ice will start absorbing energy from the table, and they'll start moving around, but they're still a solid until it gets to 0 degrees. And so they'll start moving faster and faster. They'll vibrate in place faster and faster until at 0 degrees, they will then start to turn into a liquid. So they'll start to melt. That is this melting point. Well, in that case, the molecules will start breaking apart. And when they do that, all the energy is going to melting them or breaking them apart, and so the temperature doesn't go up. All the energy is going to breaking them apart. So when you see this plateau in a phase diagram, it's because that represents a phase change, and the reason the energy is not continuing to go up is because all the energy is going to breaking the molecules apart. Now, once it's all a liquid beyond 0 degrees, then the liquid will start to heat up. Let's say we have it on a hot plate now, we're heating it up, and the molecules are moving faster and faster and faster until it gets to 100 degrees of boiling point. And then the molecules it's going from a liquid to a gas, and it's taking a lot of energy to break them apart. And so all the energy is going to breaking them apart, and so the energy doesn't go up until it all turns into a gas. And so when you say, what's happening here and here, the energy is going to breaking molecules apart, and so the temperature is not going up because of that. In these other cases, this represents a solid, this represents its liquid phase and a gas phase, and at those states you can actually heat them up, and the molecules start moving faster and faster. So it says again, which represents the melting point on anytime you have a phase diagram for anything. So there's the melting point. There it would be a solid no matter what it is. So it'd be a solid here. It would be a liquid here. And this would be the boiling point. Again, where the molecules are breaking apart, that again is the melting point. And this could be for any substance. Notice we don't have a specific temperature label. If it's pure substance, it'll have a specific melting and boiling point. And then this would be whatever that substance is, this would be when it would be a gas. And so again, you should be able to, I've labeled the diagrams for you, but you should understand how I've gone about that. And that is it for today. You have a POGIL next. Good luck.